Question 7. The diagram shows a smooth track which lies in a vertical plane. The section AB is a quarter, a circle of radius 1.8 meters with center O. The section BC is a horizontal straight line of length 7 meters and OB is perpendicular to BC. The section CFE is a straight line inclined at an angle of theta above the horizontal. The particle P of mass 0.5 kilograms is released from rest at A. Particle P collides with particle Q of mass 0.1 kilograms, which is at rest at B here. Immediately after the collision, the speed of P is 4 meters per second in the direction BC. You should assume that P is moving horizontally when it collides with Q. Part A, show that the speed of Q immediately after the collision is 10 meters per second. Okay, now I'm going to look at this section here. Okay, so that section, let me just draw it here, also here. Now at point A here, there is potential energy. Okay, I'm going to use the energy method. There is potential energy. Why is there potential energy? Because there is vertical height. There is vertical height from the horizontal. Since it is beginning from rest, then that means we don't have kinetic energy here. By the time this one comes here, it will pass here at B with a certain speed. Okay? So here at B, there will be kinetic energy, but no potential energy because now it is on the ground here. So there is no vertical height. You see that? Now, by the time P reaches point B, all its potential energy is converted to kinetic energy. As simple as that. So that means, let me actually write this: by the time P reaches point B, all its potential energy, all its gravitational potential energy is converted to kinetic energy. Now, what is potential energy? Is mgh. Then kinetic energy is a half mv squared. You can see that m disappears. And then we have g is 10, then the height is 1.8. This is a half here, then v squared. That means v is going to be, this will be 18 times 2, that is 36. So root of 36, that one will give us 6 meters per second. So this is the velocity with which P hits Q at B. Okay, now using the principle of conservation of momentum, MP UP then plus MQ UQ is equal to MP VP then plus MQ VQ. Momentum before collision is equal to momentum after collision. So we have the mass of P was given as 0.5. 0.5 then times the velocity is now this one here, which is 6. Then plus the mass of Q is 0.1, but it was at rest. It is at rest at B. Okay, collides with the particle Q of this, which is at rest at B. You see that? So times 0, the momentum is therefore 0 there. And then after collision, they said that immediately after collision, the speed of P is 4 meters per second. So we have 0.5 times 4. And then plus the mass of Q is 0.1, then times the velocity of Q is the one that we are looking for. So this one gives us a 3. So 3 here. Then we shall subtract a 2 that comes from here. And then we shall divide by 0.1. So that means VQ is going to be equal to 10 meters per second. That is that. When Q reaches C, it collides with another particle R of mass 0.4 kilograms, which is at rest at C. The two particles coalesce, so they form one particle. The combined particle comes instantaneously to rest at F. You should assume that there is no instantaneous change in speed as the combined particle leaves C, nor when it passes through C again as it returns down the slope. Given that CF is equal to 0.4 meters, find the value of theta. Now I'm going to draw another simple sketch here. We have this horizontal track. Then we have on an inclined plane here. Okay, so it is going all through like that, because if you check here, so the speed with which this one reaches here is going to be now the same initial speed it is going to start with to move up here. That is what they said, no instantaneous change. Okay, now we are having point C here. So by the time this particle reaches here, it has kinetic energy. Okay, because it is reaching there with a certain speed. You see that? Then we can also connect this one here and this one here. We form a triangle. Let me make this one dotted. So we are going to have an angle theta here. Then, of course, when it moves up to here, to F, this is 4 meters. Was it 4 meters? C to F is 0.4 meters. It is here. And then, by the time it comes here, because there is generation of this vertical height, then we shall have potential energy there. Okay? Potential energy. And they say that the combined particle comes instantaneously to rest at F. That means here we don't have kinetic energy because the velocity is what? 0. Okay. Now there is H here, which we don't know, but we know that sine of the angle is equal to the opposite, which is H, over the hypotenuse, which is 0.4. So meaning H is going to be equal to 0.4 sine of theta. Okay. So now we need to find the velocity. We need to find the speed with which this combined particle reaches here at C. Okay. Momentum before collision is equal to momentum after collision. So MQUQ, then plus, remember this one is hitting R. So MR UR is equal to, then since they coalesce, they have the same velocity. So we shall have the masses put together. So MQ plus MR, then times what? V here. So the mass of Q is of course 0.1, then times the velocity, its speed after hitting with Q, this one it was moving with, it is 10. Okay, so we shall have 10 here, and then plus this one for R, it is given as 0.4 kilograms. So 0.4, but it is at rest, so 0. And then here we have 0.1 plus 0.4, which gives us a 0.5 here, right? So this will be 0.5 V, and this one will give us a 1. So meaning V is going to be equal to 1 over 0.5, which is actually a 2. Okay, meters per second. Now, after that, we are going to have all the kinetic energy. Okay, what is the kinetic energy of the combined particle here? So, kinetic energy at C, this one is going to be a half times the mass. We have 0.1, then plus the 0.4 because it is one combined particle, then times V, which is squared here. So you have a half times 0.5, then times 4. What do we get here? This is 2, then times 0.5. That one will give us a 1. So we have 1 joule. Okay. Now, by the time the combined particle reaches F, its kinetic energy has been converted to potential energy. You see that? Its kinetic energy, yeah, this one is going to be converted to this. As simple as that. Or you can say work done by the driving force is equal, minus work done against resistance is equal to change in mechanical energy. But work done by the driving force is 0 because there is no applied force that is constantly taking the particle, okay? Then work done against resistance, this one here, we are seeing the plane. Is the plane smooth or rough? Let's check here. It is actually smooth because they say smooth track. It is all through this one here. So even here, this one will be 0, okay? This one will be 0. Then when you come this side, final mechanical energy, then minus the initial mechanical energy, you will see that the final is this one here, and then the initial is this one here. So because this is 0, then when you take this one this side, so they are equal. You see that? So that's why I'm saying, let me write it also. By the time the combined particle reaches F, all its kinetic energy has been converted to potential energy. So we say the kinetic energy, which is a half mv squared, is equal to the potential energy mgh. Of course, m will go then, but I can leave that. But we have kinetic energy, which is 1, the whole of it is 1. Then m is 0.5. Remember, we have 0.1 plus 0.4, okay? Then times the acceleration due to gravity is 10. Then times h, which h is here, you see, 0.4, then sine of theta. So this simply implies that, what will this one give us? This one is giving us 5 times 0.4, that is a 2. So 2 sine of theta, which is equal to 1, meaning sine theta is equal to a half, and then theta becomes the arc sine of a half, and then theta becomes 30 degrees. That is that. Then part C, find the distance from B at which P collides with the combined particle. Now, I'm going to also draw something here to show you what is happening. Now, we have F here. We have this combined particle here, okay? Or I can say Q has come here, but then it finds R there. This is Q, and then we are seeing that this is 7 meters, okay? This is point C, and then this is point B here, from the diagram here, okay? Now, we are going to have P here is moving. Remember, when it collided with Q here, Q moved. As Q is moving, even P is coming. So Q goes and hits R here, but also P is moving. So we need to know the time taken. After getting the time taken, then we shall be in position to get the distance that is traveled by P here. You see that? So I'm going to first start with that. So P, let's say, is around here. You see that? It is moving. It is around here as Q is moving to hit this one here. Now, time, of course, I can also continue this one, and I say this is 0.4. We have already seen that this is 30, so this is 0.4 sine of 30. That is the height here. Now, we have time taken for Q to reach R or to hit R. The time taken here, remember, when we use this one here, it is constant speed, okay? Speed times time, then there is distance here. So we shall have distance over the speed. So the distance is 7. The speed of Q after collision with P, what did we get? After collision with P, the speed of Q was 10. You see this one here? Was 10. Now, we can go back and we put 7 over 10, which is actually 0.7 seconds. Now, for T, for this T which is equal to 0.7, where is P? Okay? Distance, the distance traveled by P, traveled by P, okay, the SP on that horizontal track, it is going to be, how do you get distance? It is speed times time. So the speed, remember after collision, they also gave us the speed of P. Here it was 4, okay? So that will be 4, then times the 0.7, the time taken. This will be 2.8 meters. So P is 2.8 meters, okay, from B. Or it has traveled 2.8 out of the 7. So which distance now is left? 7 minus 2.8. P has to move this distance of 4.2 meters. Okay? So, now the combined particle, let's look at the combined particle. The combined particle, QR, call it like that. If F is equal to MA, okay, this combined particle here, remember, is moving up the plane. So this particle here has gotten no force taking it, okay? We have, let's say the particle is here, okay? No force taking it, but there is mg sine theta here, okay? So I'm going to have F, which is equal to ma, so there is 0, there is no force taking it, okay? Then minus mg sine of 30, mg sine of 30, then is equal to m, then times a. Of course, the m is going to go. This will be negative 10, then times a half, then this will be a, meaning it will accelerate with negative 5 meters per second squared. It is decelerating, that's why it is coming to rest, okay? So using v, which is equal to u plus at, we can have the final, because it is coming to rest, okay? Remember, it goes up and comes to rest at F, then comes back, okay? Let me even put this as QR. It goes, and let me take away the F here. So this particle here will go here, reaches there at F, at point F. This is the 0. Take off this and take off that. So it will reach here, but then it will have to come back. So when it comes back, passes here, it will find P along somewhere, okay? Somewhere, and then it collides with it again. So the final velocity is 0. The initial velocity is which one? Is 2. Here, the speed, we saw it. It was 2. Just here. Remember this one here? Is 2. Okay. Now, that is 2 minus, then you remember this one is minus 5. So minus 5 of t. So you have now 5t, which is equal to 2, and then t becomes 2 over 5, which is 0.4 seconds. Okay, so this is time taken by the combined particle QR to reach F. Now, since the movement here is symmetrical, the time taken to reach here is the same time taken to come back to this position here. You see? So, therefore, time taken by QR to return to C is also going to be the same, 0.4. That means QR has now traveled 0.4 and 0.4, that is 0.8. Okay? Remember, P has moved up to here. Now, Q moved here. Okay? Then it takes 0.8 to move back here. Then P is somewhere. Are we there? Then after that, then this QR is going to move back as also P is moving back. So I will therefore say that time taken by QR, okay, to return to C, so going up and also going down, okay, is going to be equal to 2 times this 0.4, which is 0.8 seconds. Now, where is P? Distance traveled by P, okay, when T is equal to 0.8. Where is it? That one is going to be, remember, it is moving with a speed of 4, then times the 0.8. This one will give us 3.2 meters. So P has added on it has added on 3.2 meters. So which distance is now left for it to travel? Remember, when you check here, now it has added on the 3.2. So when you get 4.2 minus the 3.2, then that means there is 1 meter here. So that is going to be 1 meter between these two to collide. That will be the distance traveled. Okay. So I will have, I'm going now to draw something again here. So we have, this is our track. Now QR is coming back. Okay. Then P is now here. So if we get 4.2 minus the 3.2, this one gives us 1 meter. Remember this, the whole of it is 7 meters from here to there. This is point B here, and this is point C here. So if P is now here, okay, now this one here, the QR is going to travel a certain distance, SQR. Then P is also going to move, okay, that distance there. And then they, let's say, collide here. So this is the whole distance which is going to be traveled by P here. Okay, now let's look at what is happening here. What is the displacement of P from B? The displacement here, because where these two are going to collide, they are going to be the same distance from B. Okay, so what is the displacement of P from B? So at first, remember I told you here, it had moved 2.8. Then now after 0.8 seconds, okay, it has now moved 3.2. So we are going to get this 2.8, then plus the 3, plus this 3.2, okay? So we shall have 2.8 plus 3.2. Now remember, P is moving this way with a speed of 4 meters per second. Then this one is moving this side with a speed of 2 meters per second. Okay? Now, P is here. When we get this one and we add, it is going to give us 6. So that means this is 6 meters here. Okay, 6 meters. Now, there is another smaller distance P is going to travel here. Okay, here. And then it meets with this QR here. So we shall have its speed, remember, is 4, then times the time. Now, both of them are here. So this one is taking, let's say, t, and also this one is taking t. So we shall put, let's say, plus 4t. Okay, this one is now going to be 6 plus 4t. Then let's look at the displacement of Q, this QR from B. Now, this is 7, okay? Now, minus this distance, it is going to move here. This distance is going to be 2, because the distance is going to be speed times time. So their speed is 2, then times the time taken, which is t, the same that we have taken for P here. So it will be 7, then minus 2t, okay? So that is that. Then we can say that on collision, P and QR are the same displacement or distance from B. So I'll get 6 plus 4t. I'll equate it to 7 minus 2t. Bring this one this side. That one will add up. So we shall get 6t. Then take 6 this side. That one will be a 1. 7 minus 6, that is a 1. So meaning t is going to be 1 over 6 seconds. That means these ones are going to take 1 over 6 to collide again here. Okay? When this particle QR has returned to C and it is coming back. So from there, now we can substitute in any of them. So displacement, is that what they asked? The distance from B at which P collides the combined particle. So we shall say distance from B is now going to be, we can substitute in this one here or this one here, whichever you want. So 6 then plus 4 times 1 over 6. And what does this one give us? This is 6 times 6, that is 36. 36 plus 4, that is 40. 40 over 6. So by 2, you get 20. By 2, you get 3. So it is 20 over 3. So 20 over 3, I'm going to write it just like that. Or I can say this is 6 whole number, 2 over 3. Or you can write to 3 decimal, to 3 significant figures, which will be 6.67. So this has been it for this paper. Thank you so much for watching. May God bless you. If you find the content very helpful, kindly like, share, and even subscribe. See you in the next videos.